Introducing derivatives part 2. In part 1 we started with a position function, and from that position function we found the average velocity going from time t to time t plus h. After we found average velocity, we found instantaneous velocity by having h go to 0. And by having h go to 0, that made our time interval smaller and smaller. Then we generalized this idea and we defined something that we called the derivative function. The derivative function is found with this limit process, where you first find this ratio f of x plus h minus f of x, all of that over h. You first find that ratio, then have h go to 0. So, and that's just a definition. We also said that in addition to the notation f prime, you will also see over the course of this semester other notations such as dy dx, y prime, and d sub x of y. So this is just an introduction. I know I'm throwing a lot at you, but you'll see it again and again and again. So given a position function, the derivative found using the limit process is the same as velocity. So velocity is the derivative of position, and velocity can also be written as ds dt. All right, so discussing this position function and this velocity function, let's move on to acceleration. Remember, acceleration is the instantaneous rate of change of velocity. So acceleration itself can be found with this limiting process. So let's find acceleration. Well, first remember I said that we have to find this ratio, the function velocity evaluated at t plus h minus velocity at t, all of that over h. And of course this is a terrible mess and we have to clean it up. So we distribute the negative 32 and then cancel out the things that are the same but different signs, and then we get something rather attractive looking, and here we can simplify even further, and then we take the limit and we find the acceleration to be exactly what we were hoping it would be, and that would be negative 32 feet per second per second. We also, at the very beginning of the semester, talked about how the slope of the tangent line is found with this limiting process using slopes of secant lines. And we were doing it at particular points, but what if we were to say, well, we just want to do it at some point x? Well, if we do that, then we're talking about the derivative function. So the derivative function not only gives our instantaneous rate of change, but it also gives the slope of the line tangent to the curve at x. So if I have a function f prime gives me instantaneous rate of change, but it can also tell me what's the slope of a line tangent to the graph of f at the point x. Now, it is possible to have a function defined at a point but not be differentiable at the point. We've seen that not every time we take a limit does that limit actually exist. And so let's look at some possibilities of where this limit does not exist. Well, one place is if you have a really sharp turn. If you have a really sharp turn or a cusp, then the average coming in from the left will be different from the average coming in from the right. And so the limits will be different coming from the left and the right. And you might remember that a limit doesn't exist if the left hand and right hand limits don't agree. So if they don't agree coming from the left and the right, then the limit doesn't exist. And so the function is not differentiable at that point. Also, if a function is not continuous at a point, then it's not differentiable at that point. Another possibility is the function having a vertical tangent line at a point. So your tangent line's going up and straight up and down. Well, then we say that the slope of that line is undefined, and so the function would not be differentiable there. All right, so wrapping this conversation up, f prime of x, which is found using this limiting process, gives the slope of the line tangent to the function at the point. It gives instantaneous rate of change of the function. It gives what we call the derivative of the function. It gives velocity if the function is position. It gives acceleration if the function gives velocity. Some notations that you're going to see is f prime of x, dy, dx, and y prime. And these are all found using the limit process. They all mean the exact same thing. F prime of x is equal to dy dx is equal to y prime of x. All the same thing. Now you might have noticed that computing the derivative using this limiting process, even for a relatively simple function, is tedious and time consuming. So good news, in the next section we're going to start learning how to find the derivative just by learning some rules. So we'll start that in the next section, and I'll see you then.